We are Group 1 and we're going to present statistical inference on group comparison and conditional independence today. Our goal for this project was to fit a machine learning model to a dataset, but statistical inference revealed it was not suitable for modeling. We then select a more appropriate dataset and build a Gaussian graphical model. We're going to present how we utilize statistical inference to reject our primary selection of data. In this study, we aim to analyze the distribution of SiO2 concentration, and the graph on the side shows the first 10 samples from the data. To understand the composition of a dataset, we group the data by hydrologic type and count the number of observations in each category. Since closed and reservoir has very few samples, we ignore them and focus on drainage and seepage lake. Then we create a box plot to visualize the distribution across our target to lake type. And there are extreme values in the seepage. So we remove it to ensure our data is not skewed. Then we use a bootstrap to know the distribution of the sample mean. We pretend our sample is a population and sample from it with replacement. If the bootstrap sampling is approximately normal, then means that the true sampling is approximately normal too. Therefore, inference about the mean, such as using t-test, is useful. Here's our code we use for bootstrap. We first filter it and perform 1000 resampling iteration with replacement for each group. From the histogram, we know that the distribution are approximately normal. Seepage lakes have lower mean and a wider spread. This allows us to focus to use the hypothesis t-test, such as the Welch t-test.
For the last page, we finished to justify that the original group dataset has the normal distribution. So here, then we will try to use the t-test to compare the mean of two independent groups of determine if they are significantly different. So we have two choices because we have two samples. One is the pool t-test and second is the Wilks t-test. For here, we find that the spread of two different groups are different. So we'll use the Wilks t-test. So our non-hypothesis is the mean of the group drainage and the group seepage are the same. And the alternative hypothesis is the mean for the group drainage is greater than the mean in group seepage. And we find that the p-value are 0.002, which is significantly smaller than 0.05. We can confirm that the drainage lake have significantly higher silicon dioxide concentrating than the seepage lakes. And then we can use the t-test to find the 90% confidence interval of mean of difference between the drainage and the seepage. So there are two data sets. The first one is for our original data, and the next is for our bootstrap data. So when we think about the original data, this t-test told us the 90% confidence interval for the overall means falls between 2.77 and 4.69. However, when we using our bootstrap dataset, the mean difference of the 90% confidence interval is much narrower at 3.1 and 3.22, suggesting a stable and reliable estimate.
So far, by using the bootstrap and the t-test, we have analyzed the difference in the silicon dioxide between lakes. Now we're going to use the MLE to find the best fitting normal distribution for each lake type. And here's the R code that we use. And here's the output. So we can see that the mean estimators for these two distributions are different. And because of the relatively small standard error, we can see that the estimators are pretty precise. So basically, the MLE support our findings before, and we can get the conclusion that the silicon dioxide distribution under different lakes are significantly different. But due to this mixture nature of the dataset, along with little continuous features, the dataset doesn't align well with the machine learning algorithm, which we plan to implement further. The Gaussian graphical model, which requires a higher dimensional and consistent Gaussian distribution throughout the data, is thus requiring a different dataset. And Tony and Alex will be presenting the application of this new algorithm.
Okay, thanks Shuhua, Ruoyu, and Ji for the introduction of their statistical inference application. So we'll be introducing another application which utilizes the concept of Gaussian graphical regression. We start by introducing the theory, continue by explaining how statistical inference can be leveraged in the analysis, and conclude by demonstrating the R code realization. And unfortunately, we use a different dataset due to the limited and categorical features in the previous dataset. We start by the theory section. A Gaussian graphical model, GGM, captures conditional independence relationship through an undirected graph, where the nodes represent the random variables, and the edges exist if two variables that are conditionally dependent. The reason why it's called Gaussian graphical model is because it's based on the multivariate normal distribution. And particularly Gaussian graphical regression, or GGR, is introduced to deal with covariate dependencies, which extends GGM by incorporating covariates into the conditional independence framework, and is particularly useful in high-dimensional statistics. A covariate is a variable that affects a response variable but are not of interest in the study. So here's the setup. Define the p-dimensional random vector x minus j and the precision matrix. Establish the dependency by this equation. Here we are replacing the regular response variable y in the linear regression with one of the xj variable, and conclude that the epsilon j is independent of the x minus j if and only if beta jk satisfy this equation. We then define the covariant random vector u and define the conditional distribution of x given u. Here the BH represent the contribution of the covariate effect to the precision matrix, and we have an extra assumption to make the analysis more tractable. We often use center vector, and thus the equation is rewritten as the following. Notice that we include interaction term to consider the covariates, and then in the actual implementation, consider this partition matrix, variable x1 to xp that you are interested in the study, and the covariate u1 to uq. So we apply the centering to get the matrix with z and u. So here the zj and uh are just two column vectors, one from the actual interested variables, one from the covariate. We define this beta j column vector that collects all the coefficients, and the beta jh that collects the coefficients belongs to the H group. This is only for the single regression, and we'll have p different regression tasks in total. We collect the beta and BH, and these two estimates provide two perspectives of the regression, both element-wise and group-wise. This is related to our estimation of the betas using the sparse group lasso regularization. We write this large design matrix W as the following notation, and now this multi-task learning estimate eventually come into place. Notice that the lambda E, lambda G are two Turing parameters. The regularization in this equation is known as the sparse group lasso because it combines both element and group level sparsity constraints. The beta 1 norm proposes element sparsity because the effect covariance may affect only a few edges, and the sum BH 2 norms encourages the group-wise sparsity. Notice that the regression we familiar with tend to reduce the magnitude of the coefficients, yet the lasso regression tend to make some coefficients exactly zero. So therefore, this debiasing is introduced to solve the underestimation caused by the lasso regression. However, this debiasing simultaneously presents a theoretical challenges because calculating the joint distribution is nearly impossible. So the key finding is that in order to address this problem, although the coefficients are estimated jointly, they can be debiased separately. And we propose what's called a segmentally adjusted graphical regression estimator. And the image hat is given in this form, which is an estimator of the sigma W inverse. And here are just a few definitions. So there's an alternative approach, which involves eigen decomposition and other numerical techniques. But unfortunately, due to the time constraint, I will not cover this.
Okay, thank you very much, Yitan, for explaining the theory part. Now I'm going to cover the coding implementation using R. And the dataset we choose is the Taiwanese bankruptcy prediction from UCI machine learning repository. So we choose the following 8 features as the response variables and the 3 covariates. We try to estimate the coefficients before and after debiasing to investigate if the dependency structure changes. So we use the mass, QGraph, and the SPAR Eagle packages for this analysis. We first load the data and define response variables and covariates. We first apply the sparse group lasso estimation. Here we use the existing sparse eagle function in the sparse eagle package and save the coefficients in the beta estimate list. We use 8 different sets of coefficients in the list since there are 8 response variables. Each set of the coefficients involve both coefficients of single level variables in x minus j and the interaction terms. The next step is debiasing. We use the first approach instead of the alternative one, unfortunately, due to the slow convergence rate and yield conditioning. The third step is evaluating the independence according to the estimated coefficients. Recall that we conclude that xj is independence of other variables if and only if the corresponding coefficient satisfies this equation. However, we need to consider the interaction terms as well, and therefore we evaluate the coefficients of both the single level and interaction terms based on the given threshold. The last step is to visualize, where we leverage the undirected graph. If there are edges between two nodes, it implies that there is a conditional dependence between the two variables given the covariates. Here is an undirected graph. It seems that there's no significant change before and after we debias. To sum up, we first start by introducing the Gaussian graphical model and a regression by evaluating the estimate using the Schwarz group lasso regularization before and after debiasing the estimate. Finally, we visualize the conditional independence using the undirected graph for more accessible interpretation. And that's all for the application of statistical inference in group comparison and conditional independence. Thank you for your attention.